Okay, everybody, let's go on to chapter 3 of the Navstar book, GPS applications in the United States Army Corps of Engineers. As with chapter 2, we will have a couple questions that will be part of the homework. For this, I will go over a couple of questions that you may see. Just start thinking about this now, getting it in your head early. Some of the questions will be, why does GPS need a control segment at all if the satellites already know their orbits and time? In what ways is GPS more like a continuously updated reference frame than just a constellation of satellites? How would your confidence in GNSS position change if you knew nothing about the underlying reference frame or datum? So those questions you will see, or a couple of them you'll see on your homework. We'll get into chapter 3 here. Again, I'm going to just try to do a quick video, kind of highlight just a summary, but please read this. I still have the website up, the gps.gov. Please feel free to get on that. Look for some more current information on there. I try to have some of that here, but obviously there's a lot more than I can actually get into. This website is wonderful. It has a bunch of links that'll take you to explain more information in greater detail. And as I said before, I just fall down a rabbit hole, clicking on link after link after link, just reading and reading and reading. So please, by all means, feel free in your free time, just enjoy reading all the GPS information you can get your hands on here. So within the United States Army Corps of Engineers, GPS is used to densify and maintain control networks, support mapping and construction, and provide real-time positioning for platforms and equipment. Most applications rely on differential positioning with carrier phase tracking to meet second and third order accuracy needs. So with the project control densification, GPS is used to extend existing project control and existing project control into new network areas. Try that again, see if I can edit this out. They use GPS to extend existing project control into new work areas. It replaces long traverses and running levels with shorter GPS sessions. Typical use is to set a network of control monuments for design, layout, and monitoring. Their target accuracy is a second or third order, adequate for most construction and engineering work. With the geodetic control densification, they can tie projects into the National Geodetic Reference System, the NGRS. We're going to talk a little bit later about the NSRS, the National Spatial Reference System, which probably supersedes this. There's datums that are coming, updating, that's going to affect every surveyor, regardless where you are and what kind of work you do. If you use the GNSS tools at work, this is going to affect you. We'll get into the modernization in a couple weeks. Just bring it up to your attention now. Back to the geodetic control densification. This is to establish new high-quality stations between existing NGS control points. GPS is far more efficient than classical triangulation and EDMs, total stations, over long distances. The results generally meet or exceed the FGCS second order criteria. With talking about the control densification, I should have added that as they're speaking specifically about horizontal. It's now talking about the vertical control densification. GPS is used to provide supplemental vertical control with caution. Ellipsoid heights or I'm sorry, GPS heights are ellipsoidal, meaning they go from the ground to the reference ellipse. Uh, and what projects need are orthometric heights, which we kind of generically intertwine elevation with. Kind of the same thing, height from mean sea level. That's something else we'll get into with datums, orthometric heights, um, elevation heights, geoid heights, and how they all interlace, how they all differ, and how we get an orthometric height from an ellipsoidal height and a geoid height. Conversions are required with a required geoid model and or a local benchmark pair. The vertical accuracy is weaker than the horizontal, often not a full replacement for precise leveling. The orthometric heights that can be converted are appropriate for topo mapping and moderate tolerance work, not for high order leveling. Something else they use for is structural deformation studies. Repeated GPS surveys can detect small movements of dams, levees, and bridges. Baseline comparisons over time reveal translations and rotations in 3D. GPS can offer millimeter to centimeter level detection over broad structures. Another way they use it is for photogrammetry support. GPS provides ground control points for aerial photogrammetry. Greatly reduces field time compared to purely conventional photo control. This directly supports orthophoto and DEM generation with known absolute accuracy. The dynamic positioning and navigation, real-time GPS, often the RTK, is for hydrographic survey vessels, dredges and construction equipment, and other moving platforms. This enables accurate guidance, track logging, and production monitoring. The GIS integration. So GPS-derived coordinates feed directly into GIS and mapping systems and drop it into a real-world position. Provides precise, consistent locations for assets, facilities, boundaries, and monitoring points. GPS-based control underpins long-term geospatial quality. So again, I'll read through a couple of these questions I want you to think about as you're reading this. Why does GPS need a control segment if all the satellites know their orbits and times? In what ways is GPS more like a continuously updated reference frame than just a constellation of satellites? And how would your confidence in a GNSS position change if you knew nothing about the underlying reference frame or datums? Okay, so that's going to wrap up the quick little lecture here for Chapter 3. I'll have another short lecture, hopefully a nice short lecture, for Chapter 5.